No, that's normal. That's normal.
I'm bad like a Barbie. I'm a doll.
Anyways, the way I'm gonna solve this is we have a passenger in an elevator.
Oh, interesting.
So the elevator starts from rest. So our initial velocity is 0 meters per second.
Oh.
It moves upwards with a constant acceleration, and it moves 1 meter
1 meter
in the first 2 seconds.
in the first 2 seconds.
A passenger in the elevator is holding this 9.4 kilogram bundle at the end of a vertical cord. We're trying to figure out what is the tension in the cord as the elevator accelerates. So we're trying to solve for a force, the force of tension. So I'm going to start off with a free body diagram for the object that is connected to the rope that has tension in it. We only have the mass of the hanging object, so that's the one I'm going to include. We have the force of gravity, and we have the force of tension. I'm making the force tension greater than the force of gravity because we need more upward force than downward force in order for this thing to be accelerating upwards. So we have our sum of our forces is going to be equal to that force tension minus our force gravity. So we're trying to get force tension by itself, so we're going to need to make sure that we know this and this. Are you recording a video of this?
What?
No, she's not.
I would never.
She would never. She's silent lip syncing to the Marvel song.
That's too bad. No, seriously, are you?
Yeah.
Okay, cool. Send it to me. I'll upload it to the YouTube channel.
Wait, actually?
I don't want to record this again. I'll post it there.
Okay, can you
We'll
you're gonna have
in this
some
whole thing.
commentation or
I
whatever.
am commenting right now.
No, but by me.
Singing.
So anyways, some of the forces is mass times acceleration. Our force tension
I
is
need
what
to
we're
make
solving
an intro for you.
The force gravity is mass times our gravitational field strength. Okay? So because we're trying to get Ft by itself, I'm just going to add mg to both sides. So ma plus mg is going to be equal to our force tension. By the way, I'm leaving this completely algebraic because everyone would have had a different mass than me, probably different acceleration than me, so I'm just trying to keep that as generic as possible.
Okay.
Also, it's kind of useful because if you see this problem again, since you already saw it once with the lab,
Like a YouTube video.
you just get to agree use your work. Just to kind of make some things easier, I'm just going to factor out the mass. So mass times acceleration plus gravity, gravitational acceleration at least, is equal to our force of tension. Now for me, I know the mass. The mass of my system is 9.4 kilograms. My acceleration, I don't know yet. And my gravitational field strength, or the gravitational acceleration, is 9.8 meters per second squared. So I need to solve for my acceleration before I can come back and solve for my Ft. So this is where I'm going to have to use my kinematics. I am provided with all of this information. I need to solve for the acceleration here. Yeah, I have a lot of our kinematics equations over on the whiteboard over there. I'll write them up here. Just to get it in frame, I'll put up the important ones, okay? So, the one we learned from the ramp lab, that was the combination of the buggy lab and the ramp lab, is our position was equal to our starting position plus our starting velocity times time plus 1/2 times the acceleration times time squared. Then the next one that we would have is going to be our velocity is equal to our starting velocity plus our acceleration times time. And then the last one that we're really focusing on is going to be our final velocity squared is equal to 2 times the acceleration times the displacement plus our starting velocity squared. These equations only work if the object is undergoing uniform acceleration, which is going to be the case in this situation. Now, for the variables that we have a change in position, we have a time, we have a starting velocity, we're trying to solve for an acceleration. What we do not have is our final velocity. But we don't really need to solve for that. We would if we wanted to use this equation or this equation, but I'm just going to say no and no, because this one should probably be able to suffice. We know the final position is 1 meter if the starting position is 0 for that displacement of 1 meter. We know the starting velocity is 0. We know the time is 2 seconds. We know the number 1/2. We're solving for the acceleration. We know the time is 2 seconds. So we can use this equation to solve for our acceleration. So position is equal to starting position plus starting velocity times time plus 1/2 times at squared. Acceleration times the square of time. I'm going to subtract x naught from both sides, and then basically say that is going to be my displacement. That is equal to, if it starts from rest, this term can go away. So really it's 1/2 at squared. To get the acceleration by itself, I will multiply both sides by 2. So it's 2 times our displacement is equal to the acceleration times the square of time. And our acceleration can then be 2 times our displacement over t squared. Just so that way I'm trying to keep this as algebraic as possible, I can take what acceleration is equal to and plug it in here. So that way my force tension is going to be equal to my mass times 2 times the displacement over the square of time plus the gravitational acceleration. I'm going to leave it here for right now because once again, the way that the UT homework works is it randomizes the mass, the displacement, and the time for you. So, but not really the concept. So really, if you just use this equation for this specific problem, you should be able to get your force tension.
The viewers want more.